Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for May-June 2018 variant 1. So let's get started. Question 1 says figure 1.1 shows speed time graph for a vehicle accelerating from rest. Part A says calculate the acceleration of the vehicle at time 30 seconds. So this is 30 seconds. We need to use the gradient of the graph, but this part of the graph is a curve, so we need to draw a tangent in order to get the gradient at this point. So if we draw, for example, a line like this, just touching the graph at that point, we can say that this is a good tangent. Not all of you will draw the same exact line or take the same exact points. In this case, I will just take this point as point 2 and this point as point 1, and we have y2 and y1 26 and 10, and we have x2 at 60 and x1 is at 16. So first we write down the equation that the acceleration is equal to the gradient, and then we substitute 26 minus 10 as y2 minus y1 over 60 minus 16 as x2 minus x1. That gives an answer of 0.363636 recurring. So we approximate that to two significant figures because the graph can give us two significant figures. So we write the answer as 0.36 and the unit is meters per second squared. Part B says, without further calculation, state how the acceleration at time t 100 seconds compares to the acceleration at time 10 seconds. Using ideas about forces, explain why any change in the acceleration has occurred. So at first, the acceleration was decreasing. So at 100 seconds, we have the gradient low, and at 10 seconds, we have the gradient high. So at 10 is greater than 100, or at 100 less than 10. And that is due to the air resistance increasing with speed. So the resultant force is actually decreasing against the motion. So we say that acceleration at 100 seconds is less than at 10 seconds. And then we say that as the speed of the vehicle increases, air resistance increases, so resultant force decreases, and this decreases the acceleration. Part C says determine the distance traveled by the vehicle between time 120 seconds and time 160 seconds. In a speed time graph, we can get the distance by calculating the area under the graph. So from 120 seconds to 160 seconds, that would be this area, which is a trapezium. We have one base on this side equal to 20, and the other base is on the other side parallel to it, that's 30, and the height is from 120 to 160, that would be 40. Then we say that the distance is equal to the area, and we say that the average base, which is 30 plus 20 over 2 multiplied by 40, will give us the distance. This gives a distance of 1000 meters, or 1 times 10 to the power of 3 meters. Question 2 says figure 2.1 shows a forklift truck lifting a box. The electric motor that drives the lifting mechanism is powered by batteries. State the form of energy stored in the batteries. That would be chemical or chemical potential energy. Part B says the lifting mechanism raises a box of mass 32 kilograms through a vertical distance of 2.5 meters in 5.4 seconds. Calculate the gravitational potential energy gained by the box. So GPE is equal to mgh. And we substitute 32 kilograms by 9.8 by the distance 2.5. This gives an answer of 784 joules, or we can approximate it to 780. Double I says the efficiency of the lifting mechanism is 0.65 or 65%. Calculate the input power of the lifting mechanism. So the efficiency is equal to the output power over the input power. So 0.65 is equal to the energy 784 divided by the time 5.4 to get the power. This is the output divided by the input power. And then we place the input power on the other side to be the subject of the formula. Then we divide by 0.65. This gives an answer of 223.3618. So we can approximate that to 220 watts. Question C says the batteries are recharged from a mains voltage supply that is generated in an oil-fired power station. By comparison with a wind farm, state one advantage and one disadvantage of running a power station using oil. The advantage is that oil is available and it's also reliable and does not depend on weather compared to wind turbine. And disadvantage is that it is polluting or non-renewable, or that it has a high running cost. Question 3 says a rectangular container has a base of dimensions 0.12 meters by 0.16 meters. The container is filled with a liquid. The mass of the liquid in the container is 4.8 kilograms. Calculate first the weight of the liquid in the container. W is equal to mg. So I multiply 4.8 times 9.8. That gives an answer of 47.04. We can approximate that to 47 kilograms. Double I says the pressure due to the liquid on the base of the container is required force over area to get the pressure. The force is the weight, so 47.04 divided by the area, which is the multiplication of the dimensions, length and width, 0.12 times 0.16. That gives an answer of 2450. We can also approximate that to two significant figures according to the question's numbers. So we have 2500 Pascal. Part B says explain why the total pressure on the base of the container is greater than the value calculated in AII. We only calculated the pressure due to the liquid, but there is an atmosphere around the liquid that acts downwards on the surface of the liquid in the container, so we can say due to atmospheric pressure acting on the liquid or the container. Question C says the depth of the liquid in the container is 0.32 meters. Calculate the density of the liquid. We can use pressure is equal to rho gh, and we have the pressure 2450. The density is unknown, g is 9.8 and the depth is 0.32. So we divide by this bracket on the left side. The density will be equal to 781.25. We can approximate that to 780, and the unit for density is kilograms per meter cubed. Question 4a says describe the movement of the molecules in a solid and in a gas. In a solid, they vibrate about a fixed position or in place. For a gas, molecules move randomly at high speeds, and it's speeds, not speed, because they have different speeds. Part B says a closed box contains gas molecules. Explain in terms of momentum how the molecules exert a pressure on the walls of the box. We can start by saying when molecules collide with the walls and rebound, there is a change in momentum which exerts a force over the area of the walls. Question 5a says a ray of light in air is incident on a glass block. The light changes direction. State the name of this effect. This is called refraction, and the cause of this effect is the change in speed of the light or the light wave as it goes from medium to medium. Question B says figure 5.1 drawn to full scale shows a thin converging lens of focal length 3.5, and we have every 5 small squares on the grid is equal to 1 centimeter. Question I says on figure 5.1 mark each of the two principal focuses and label each with the letter F. So a distance of 3.5 from the center of the lens. This is 2 centimeters, 3 centimeters, and this is 3.5, so this is F. And we measure the same distance from the other side. This is 2, this is 3, and this is 3.5. So we label this point also F. Double I says an object O of height 4.4 centimeters is placed a distance of 7.5 centimeters from the lens. On figure 5.1, draw rays from the tip of the object O to locate the image and draw and label the image. So we need at least 2 rays to intersect to form the image. The first ray is easy. We draw a straight line from the tip of the object to the optical center, and it passes straight through without bending, and we extend it as long as we can. The other ray is parallel to the principal axis, so here it will be horizontal until it reaches the lens, or the center of the lens. And from this point we draw a line that goes through the focal point on the other side of the lens, and we extend that line until it intersects with the other line. So this is the final shape of the diagram. We have the intersection point approximately at this point, and we draw the image as a vertical arrow. And since these rays exited the object from the tip of the arrow, then this forms also the tip of the arrow. So this is the image, and the rays of light were moving in this direction and then this direction after the lens. Triple I says determine the height of the image. We use the grid to do that. We have 5 squares, 5 squares, 5 squares, that's 3 centimeters until now. This is approximately 4 centimeters from the principal axis to the tip of the arrow. Not all of you, by the way, will get the same exact value, but I'm going to write what I've measured, 4.0 centimeters. IV says state and explain whether the image is real or virtual. It is real since it is made of intersection of real rays, not extensions, or we can say that it can be formed on a screen. Question 6a says figure 6.1 shows wavefronts approaching a gap in a barrier. On figure 6.1, draw 3 wavefronts to the right of the barrier. So this will cause a diffraction, and it will be a curved diffraction since the gap is almost equal to the wavelength, or it is a narrow gap. First, we need to continue the direction of motion of the waves. So we continue this horizontal line like this. And then we label equal distances. The distance between two wavefronts here is 0.5 centimeters, so we mark distances 0.5 centimeters apart, and we have 3 wavefronts after the gap, but we use the last one that did not exit the gap as the center of the curves. So first we have a line here in the barrier. So first we have a line here that is at the edge of the barrier, and then we use a compass to draw the circular curves, zooming in to enlarge the image. So we use this point as a center, and then we measure the distance to the first point that we've marked, and then we draw a curve. This is not an exact value, but moving on to the next one, to the next point, and we draw another curve which is wider both ways. Then we increase the distance to reach the next point, and we draw another curve wider both ways again. So this is the final shape of the diagram. You can keep the central line of the direction of the wave, or you can erase it. It does not matter. Part I says figure 6.2 shows the gap in the barrier increased to 5 times the gap in figure 6.1. On figure 6.2, the new one, 3 waves are required on the right side of the barrier. Again, we have to extend the line of the direction of the wave to measure the distances between the wavefronts. And again, the distance here is 0.5 between each wavefront and the next. So we mark equal spaces. So we have here, 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 and here. We have 3 after the barrier. Now we draw the wavefronts. This is the first one inside the barrier. And the others are also straight lines since the gap is very wide. The second one here and the third. But we draw curves at the ends of these lines, and these curves are expanding from both sides, showing that there is some spreading, but it is not as much as the one in the original diagram. Question B says, describe with a labeled diagram an experiment using water waves that shows the reflection of wavefronts that occur at a straight barrier. First, we can draw a rectangle representing a ripple tank and another rectangle representing an oscillator or a vibrator that will produce the waves on the water surface, and an inclined straight line to represent a reflecting surface. We can hash the backside of that reflecting surface, and we label this is a ripple tank. We have here a barrier and an oscillator or vibrator, and the waves will move in this direction until they hit the barrier and then reflect like this. So this is the original direction, and this is the reflection direction. We can also draw wavefronts as straight lines perpendicular to the directions of the waves, approximately equally spaced. We do not have to be precise in this diagram, and we draw the reflected waves perpendicular to the new direction. We can say under the diagram, set up a ripple tank as shown, and use a flashing light or a strobe light with the same frequency as that of the oscillator. That will cause the shape of the wavefronts to appear as if they are not moving, so that the wavefronts appear to be not moving. Question 7a says, state in terms of their structure why metals are good conductors of electricity. That is because they have free moving electrons or free electrons, which allow flow of current. Part B says a cylindrical metal wire W1 of length L and cross-section area A has a resistance of 16 ohms. A second cylindrical wire, wire B, having length L over 2 and cross-sectional area 2A is made from the same metal. Determine the resistance of W2 at first. We can use a ratio or a fractional relationship. Resistance is proportional to length and inversely proportional to area, so we can say that resistance 2 over resistance 1 is equal to the ratio of length 2 over length 1 multiplied by area 1 over area 2. since it is inversely proportional to area. Resistance 2 is unknown. Resistance 1 was 16. The new length is half the original length, so 0.5 L over L. And the original area is A and the new area is 2A. We can cancel L with L and A with A. We have on the right hand side 0.5 over 2, and then we can multiply by 16 on the other side to get R2 as subject. This calculates as 4 ohms or 4.0 ohms. Double I says calculate the effective resistance of W1 and W2 connected in parallel. So we can use product over sum, 16 times 4 over 16 plus 4. That gives an answer of 3.2 ohms. C says the parallel pair of resistors in BII is connected to a battery that is made of 3 cells in series, each of electromotive force E. There is a current in each resistor. State the EMF of the battery as a whole. Since we have 3 cells in series, the voltage adds up, or the EMF adds up. So E plus E plus E, that is 3 times E. Double I says the current in the battery is IB, the current in W1 is I1, and the current in W2 is I2. Place a tick in one box to indicate how these 3 currents are related. Starting from the largest current to the last current, they are not all equal since they are connected in parallel. The largest current must be the current in the battery, so it is either this one or this one. And then the resistance with higher value takes the lowest current, and R1 was the higher resistance, so I1 would be the lowest current, so this is the lowest current, so we tick this box. Question 8 says, in a laboratory at normal room temperature, 200 grams of water is poured into a beaker. A thermometer placed in the water has a reading of 22 degrees Celsius. Small pieces of ice at 0 degrees Celsius are added to the water one by one, and the mixture is stirred after each addition until the ice has melted. This process is continued until the temperature recorded by the thermometer is 0 degrees Celsius. The total mass of ice added to the water is found to be 60 grams. Part A says the specific heat capacity of water is 4.2 joules per gram degrees Celsius, and this is in grams, and the mass given at the start of the question is also in grams, so we leave it as it is. Calculate the thermal energy lost by the water originally in the beaker. We can use Q equals mc delta theta. The energy is equal to 200 multiplied by 4.2 multiplied by the difference between 22 and 0, so it's 22. This gives an answer of 18,480 or approximately 18,000 joules. The rest of the question includes latent heat capacity, which was removed from the syllabus, so you can skip this part. Part B says assume that all thermal energy lost by the water originally in the beaker is transferred to the ice. Calculate the specific latent heat of fusion of ice. We use the equation Q is equal to mL and L is equal to Q over M. The energy is the one we calculated in the previous question, 18,480, divided by the mass of the ice, which was 60 grams. This gives a value of 308 joules per gram. Question C says, suggest a reason for any inaccuracy in the value of the specific latent heat of fusion of ice. Calculated in B, assume that the temperature readings and the values for the mass of the water and the mass of the ice are accurate. Since the ice is at 0 degrees Celsius or the temperature of the experiment is lower than the room temperature, we say that heat is gained, not lost, from the surroundings. If the temperature was higher than the surroundings or the room temperature, then heat will be lost to the surroundings. Question 9a says a student wants to demagnetize a permanent bar magnet. She suggests these steps. Place the magnet in a long coil, switch on a large alternating current in the coil, switch off the current, then remove the bar magnet. So the problem is with the last steps. State and explain whether the steps will always be able to demagnetize the magnet or not. We say no, because the magnet will be magnetized according to the direction of the current at the time we switch off the current. So we can write that the bar magnet or the bar will be magnetized according to the final direction of the current. And then we say the correction. Instead of switching off the current and removing the bar, we say the bar should be removed from the coil while the current is still working or still on. Question BI says figure 9.1 shows a coil supplied with current using a split ring commutator. connected to a battery. State and explain any motion of the coil. The coil will rotate, but we need to know in which direction. We have the poles of the magnet and we have the polarity of the battery. The current goes from the positive side, moving in this direction, and going into the page from this side and out of the page from this side to go back to the battery from the left hand side. So using Fleming's left hand rule, the magnetic field is pointing to the right, so we point the index finger to the right, and if the middle finger is pointing out of the page, we can use this side of the current, which is pointing out of the page. This part of the coil experiences an upward force according to the thumb. So this side goes upwards and the other side will go downwards since there is an opposite current on the other side. This rotation is clockwise. So in the explanation we have a lot of marks, so we first explain why is there a force in the first place. We say that the two magnetic fields from the current and the magnet interact and produce opposite forces, upwards and downwards, on opposite sides of the coil. This is called a couple, which causes the coil to turn due to the moment or the torque, and then we say the direction clockwise. Double I says the coil in figure 9.1 consists of 3 turns of wire. The magnetic field strength of the magnet is M. With a current of 2 amperes in the coil experiences a turning effect called T. The first row of the table 9.1 shows this data, and then we have changes to the data. Complete table 9.1 to give the turning effect for the changes made to the arrangement shown in figure 9.1. We could change the number of turns of the coil or the current in the coil or the magnetic field strength. So going from the first one to the second one, the number of turns stayed the same, but the current here was multiplied by 4 from 2 to 8, and the magnetic field did not change. So if the current is multiplied by 4, the turning effect will also be multiplied by 4, and we have that option here. From the first one to the third one, the number of turns was multiplied by 2 from 3 to 6. The current did not change, the magnetic field strength did not change. So if the number of turns is multiplied by 2, the turning effect will also be multiplied by 2, and we have that option here. Going from the first one to the last one, the number of turns stays the same, the current stays the same, but we have half the strength of the magnetic field, so we will have half the turning effect, and we also have this choice here. Question 10a says, explain why the voltage of the supply of the primary coil of a transformer must be alternating so that it creates a changing magnetic field to cut the secondary coil, or to create a change in flux in the secondary coil and induce an EMF or voltage. Part B says figure 10.1 shows a transformer. There are 8,000 turns in the primary coil of the transformer. The primary coil is connected to a 240 volt main supply. A 6 volt lamp is connected to the secondary coil, operates at full brightness. That means that it takes 6 volts from the secondary coil. Calculate the number of turns on the secondary coil. We use NS over NP is equal to VS over VP. NS is unknown, NP is 8,000, the primary. VS was 6 and VP is 240. Then we do cross multiplication, 8,000 times 6 over 240. That gives an answer of 200 turns. Double I says the current in the lamp is 2 amperes. The transformer operates with 100% efficiency. Calculate the current in the primary circuit. We can use the idea of input power is equal to output power, or VI in primary is equal to VI output secondary. The input voltage was 240 and the input current is unknown. The output voltage is 6 and the current is 2. Then we divide by 240 on the right hand side. To get IP, it will be 0.05 or 0.050 ampere. Part III says the primary circuit contains a 2 ampere fuse. Calculate the maximum number of lamps identical to the lamp in double I, which takes 0.050 amperes at 6 volts. That can be connected in parallel, so we keep adding the currents up according to the number of parallel connections in the secondary circuit without blowing the fuse, which means the total number of the lamps multiplied by the current in one lamp must be equal to the fuse rating or less. So we can divide the total current in the fuse over the current of 1 lamp to get the number of lamps. That gives an answer of 40 lamps. Question 11 says radon 222 is radioactive. It can be represented as Rn 222 and 86. For a neutral atom of radon 222, state the number of protons. We can get it from the proton number 86, and for a neutral atom the number of electrons will also be 86, and the number of neutrons is 222 minus 86, nucleon number minus proton number. That gives an answer of 136 neutrons. Part B says a radon 222 nucleus decays by alpha emission to a polonium nucleus. Complete the equation for the decay of radon 222. First we have the alpha, which must be memorized with numbers 4 and 2, and then we decrease the number of nucleons by 4 for the new element to 18, and then decrease the proton number by 2 for the new element, so 86 minus 2 is 84. And the symbol was given in the question PO. Question C says radon 222 has a half-life of 3.8 days. At a certain time, a sample contains 6.4 times 10 to the power of 6 radon nuclei. Calculate the number of alpha particles emitted by the radon, which means the number of nuclei that decayed, not the remaining number, for a total time of 7.6 days. Since we have the total time and we have the half-life, we divide the total time by the half-life to get the number of half-lives passed. That gives 2 half-lives. This means that we will divide by 2 twice. So starting with 6.4 divided by 2, that gives us 3.2 as an answer. Then divided by 2 again for the second half-life, that gives us 1.6. So the remaining is 1.6 and we started with 6.4. So the number of decayed nuclei is 6.4 minus 1.6. That gives an answer of 4.8, but times 10 to the power of 6 here. So times 10 to the power of 6 also in the answer. So this was the end of the exam. I hope you enjoyed this video and found it useful. If you did, give it a thumbs up and subscribe to the channel, and I will see you in another video.